Thank you. First of all, thank you for the opportunity to give this talk and for inviting me. I'm very happy to talk about some of my recent work. So to locate myself, I had my PhD in public health biostatistics in 2020 at the University of Bordeaux in France, where I developed joint models for oncology. Then I spent 4 years in Saudi Arabia. I was invited by the INLA methodology development group to develop biostatistical models with INLA. So that will be the topic of my talk today, these 4 years of work. And now I'm back in France at home as a permanent research scientist at the National Institute of Health and Medical Research. So the topic for my talk today is about what I have done with INLA for biostatistics. And this is all summarized in a book that I have just finished writing. So this book is called Bayesian Survival, Longitudinal and Joint Models with INLA. It's currently in production, so it should be published within a few months, hopefully. And when published, this book will be freely available online. So the idea of my talk today is to kind of give a good presentation and big picture of what we can do with INLA for biostatistics, and this will be tailored on the structure of my book. So yeah, the idea of INLA is that we can fit some regression models, and in biomedical research, we have some data of interest. Usually time to event data, where we have this incomplete information due to censoring, so we need some specific models like proportional hazards regression models. We have longitudinal data, where we have repeated measurements, so this hierarchical structure in the observed data, which is usually fitted with mixed effects regression models. Sometimes we have interest in multivariate outcomes, where we can have multiple longitudinal, multiple survival, or both, and we are interested in modeling them simultaneously with joint models. And spatial autocorrelation, health outcomes often exhibit spatial patterns that can be directly related to environmental factors, but it can also be the consequence of unobserved factors such as socioeconomic disparities. So this is an important point too, and those 4 points are basically the 4 main chapters of my book. So we will go through each of these points during this talk. And the reason why I did this is because traditional Bayesian samplings and iterative methods, they are powerful, but they reach some limitations for the most complex models. When you have a lot of data or when you have a lot of parameters, you easily get into very long computation times or convergence issues, and that's what I tried to tackle with INLA. So INLA stands for Integrated Nested Laplace Approximations, and it is a fast, accurate, and deterministic alternative to MCMC, but INLA is tailored for a specific class of models named latent Gaussian models. So INLA can do only a subset of what MCMC can do. It's more specific, but fortunately, many models fit within the latent Gaussian model framework, and therefore can be fitted with INLA. So to be a latent Gaussian model, a model must be expressed this way. You can recognize on the left the posterior distribution of the model parameters. That's the target of inference. Then we have the likelihood of the data. So the observed data Y has some likelihood, for example, Poisson for count, binomial for binary. So any likelihood is fine. We don't have any limitations for the likelihood in INLA. We have the prior over the parameters. Again, the priors with INLA, we don't have limitations. Any prior is fine, but the structure of a latent Gaussian model rely on this part in the middle that makes it different from standard Bayesian inference. This is called the latent Gaussian field, and it includes pretty much anything Gaussian. So in a linear regression, for example, your fixed effects, usually they are assumed Gaussian, they belong to the latent Gaussian field. Random effects, most of the time, they are assumed Gaussian, we put them here. And INLA is actually very efficient because it uses some nice mathematical tools for multivariate Gaussian, and that makes the model fit much faster than with MCMC, and it's also very accurate. When we hear approximation in INLA, sometimes we can think, oh, okay, it may be fast, but there is a trade-off. Like in variational Base is fast, but when it comes to uncertainty quantification, then you're a bit in trouble. It's difficult to get good uncertainty quantification. With INLA, we get both fast and accurate. So that's a really strong statement, but I will prove it during this talk. So the main limitation of INLA is if your model cannot be expressed this way, you cannot use INLA. So you have to rely on MCMC or whatever. So for example, if I want non-Gaussian random effects, I cannot use INLA. So many models for biostatistics, they fit with this framework, and that's what I have been developing over the 4 years I spent in the INLA development group. So just to give you an idea of the computational advantage of INLA, this is some work we did with Danilo from your group as part of a tutorial in biostatistics we published in Statistics in Medicine. We compared INLA with two MCMC approach. So first JAGS, which gives a sampler, and STAN, which is Hamiltonian Monte Carlo. And as you can see, INLA is much faster. And if you look at the paper, we also compare the result. We get exactly the same result. So INLA is faster, like around 20 times or 100 times faster here. But as the model complexity increase, multi-state joint model, multivariate joint model, it's even better. Here it's 300 times faster. So the scaling is in favor of INLA, and that allows to go beyond the previous limits in terms of complexity. We can do much more in terms of data size, but also in terms of number of parameters. So it's really interesting. It's not a small difference. It's a completely change of paradigm. So the main limitation of INLA is that it's a general algorithm and it has been widely developed for spatial and spatiotemporal analysis. It's not meant for biostatistics. So when you want to define a joint model or a multivariate joint model, the code can be a bit cumbersome and error prone. It's quite difficult to write those models within the INLA syntax. You need to be familiar with how INLA works, and it's easily cumbersome. It's not very complex, but it's a bit of a long code for those models. So we decided to develop a new R package named INLA Joint, and the whole point is just to have a user-friendly interface that comes on top of INLA for biostatistics. So for the analysis of time-to-event data and longitudinal data. So this package, it uses this building block syntax that allows to include multiple models together in the same joint model. And I'm using the syntax that biostatisticians using R are quite familiar with, like LME4 and survival for longitudinal and survival respectively. So the structure of the main function in INLA joint to fit regression models is joint. That's the name of the function. And then we can give formula. So if we want a survival model, we use the argument form serve, formula for survival, and we can make it a list to have multiple survival models. So here the first one will be defined by inla.serve. This is exactly the same as the serve function for survival. It is used to define the survival outcome. So survival outcome is defined by some time and some event indicator. So this is the same as serve, and it defines the outcome of the regression model. And here it's a function of a single covariate treatment. And then we have a second survival model, etc. We can also include longitudinal models with the form long, formula for longitudinal, which again can be a list of multiple models, each one being a mixed effects regression model with the same syntax as LME4. So for example, y is a function of the fixed effects of treatment by time, and I include random effects between parentheses. So here a random intercept and a random slope for each individual. Finally, we can link the survival and longitudinal through association. So I will give more details on this later, but here I have a list of associations. CV stands for current value, meaning the survival depends on the current value of the longitudinal. So this is just to give you an overview of the framework, but I will go in details for each of those. Let's start with survival data analysis. So the point is to give you an idea of what we can do with INLA in terms of survival data analysis. Of course, the main tool will be proportional hazards. We don't do the partial likelihood approach because we are interested in computing survival probabilities most of the time, and also because for more complex models like joint models, we need to know the baseline. So we are not interested in this partial likelihood, and we need to approximate the baseline hazards. So we have several options, parametric baseline like Weibull, but the most interesting one will be the semi-parametric baseline, which is based on random walk. So this is kind of a let the data speak approach, such that the data will drive the baseline hazard, and we have a smoothness constraint because of the random walk. So this is similar to what people are usually doing with splines. For example, in my lab, they use a lot of those M splines, which integrate to I splines, so it's convenient computationally. We did a comparison of our approach with this one, the splines for the baseline, and we find unbiased result, but also lower uncertainty. So we are more accurate than the traditional splines, which are a bit less flexible. So this is a very nice approach for baseline hazard because also it relies only on one parameter, one hyperparameter, for the variance of the random walk, so it's very efficient. Time-dependent covariates, we can handle any time-dependent covariate, whether it's measured at specific times, so we can have a stepwise evolution, or we can have very fine resolution, like every 0.01, a different value. We can handle this in any survival model. Interval censoring is also a feature. It's only available for parametric baseline. We could do it for semi-parametric. It's a bit more involved, so I'm waiting for someone to ask to develop it, but for now it's available in parametric baseline. And we have some specific models like cure fraction, where when there is a part of the population that is assumed to be cured. Stratified proportional hazards, when the risk is proportional conditional on a categorical covariate. And frailty models for recurrent events or when the data is grouped. This is for one event, but we have also situations when we observe multiple events. So the main class of models will be the multi-state models, which we can do in INLA, and the specific case of competing risks. We can also do joint frailty models, where the frailty term from a frailty model can be shared in another survival model. We can have multiple frailty models sharing in multiple terminal event models, so it's very flexible, and this is based on shared random effects. This is not really a limitation. We could also assume the risk of one event depends on the risk of another event, so having dependence over the entire linear predictor. This is feasible, but I'm focusing on the gold standard, so shared random effect is the basis, but we have flexibility. We could develop other approach for multiple events. So let's look at one example. Consider competing risks. Assuming we have two different competing risks, one or two, k equal 1 or 2, and we want to fit risk-specific proportional hazards models. So the risk for individual I and outcome k at time t is defined by some baseline risk-specific baseline hazard and the effect of some covariates. Here I only include treatment. So I simulated some data from this model. You can see the data here. For example, the first individual after 0.41 unit of time as the event 1. So this is the event indicator for the first event and the second event in green. And then we have the covariate treatment. So individual 1 has the first event and it is censored for the second one because it's a competing risk. Individual 3 as the second event is censored for the first one, and some individuals may be censored for both. So basic survival data. To fit this model, we load the INLA joint library, and then it's just a joint call where we give the formula for survival as a list with two formula for our two competing risks. And that's it pretty much. You just give the data, and then you can get your summary. So here the summary is structured for each outcome. We have the results. So the first one is the variance of the baseline risk. So we don't really interpret this parameter. Usually we just look at the shape of the baseline risk, which is available as a plot. So if you plot this, you will get the trajectory of the baseline hazard. And then we have the effect of covariates. So here only treatment has an effect on each of the risk-specific submodel. Usually we don't really interpret this value. We have more interest in hazard ratio. So with INLA joint, you can simply convert to hazard ratio by adding HR equal true in the call of the summary, and you will directly get your hazard ratio with the uncertainty on this scale. So here we have the hazard ratio of treatment on the first risk and on the second risk here. So I want to introduce now one very important feature of INLA joint, which is the predict function. We can do many things with it, among which computing survival probabilities, because we are modeling the risk and we can convert it into probabilities. We can generate patient-specific predictions when the model is at the individual level. We can compute marginal predictions for specific covariate profiles. We can quantify uncertainty. All the quantities that the predict function computes are accompanied with uncertainty quantification. And I tried to keep the syntax as simple as possible. So you have your model, the new data for which you want to predict, and the horizon of the prediction, basically. So if we get back to this competing risk model, we could be interested in computing something out of it. Here we have the risk. Usually we compute survival probabilities based on the risk by integrating it. But with competing risk, it's not really meaningful because survival would give the probability of observing an event in a world where you don't have the risk for other competing events, which is not so interesting. With competing risk, usually we want to compute the cumulative incidence function, which gives the probability of observing one event, assuming you do not observe any of the other competing events. So to compute this, we can use the predict function. basically what we do is we create a new data for the scenario we want to predict for. So here it's a very simple data set, only 2 lines. One is for treatment equal 0, and one is for treatment equal 1. And we want to compute the probability of event conditional on treatment. So I call my predict function, I give my fitted model, I give my new data, which is basically this small data set, 2 lines, 2 columns. The horizon of the prediction, I want to predict until time 4. Then the ID to define the different scenarios, here only 2. And I ask for cumulative incidence function. If I remove this, I will get predictions of the risk. If I put survival equal true, I get my survival probabilities. But for computing risk here, I want cumulative incidence functions. So that's how you do it. And then I can directly plot the output. So this is the result. We have the cumulative incidence function conditional on treatment for each of my 2 competing risks. So for example, the first risk, at time 3, we have a probability of 0.5 to observe it. And for the second, for treatment equal 1, the probability is 0.75. So it's very easy to interpret. We directly get the result as we want, and we don't have to do post-processing. So that's one advantage of INLA joint also. Beyond helping fitting models with INLA, we have also those post-processing functions. Okay, so now let's discuss a little bit about longitudinal data analysis. So we have also some options. Of course, the main one will rely on mixed effects models. That's the core of longitudinal data analysis. And in particular, we have the family of generalized linear mixed effects model that includes all the families from the exponential distribution, so Poisson, binomial, gamma, beta, etc. We have other specific likelihoods, like proportional odds model for ordinal data, or zero-inflated data models like the hurdle, 2-part or 2-bit model. One important point, we can include pretty much any function of time. We are not limited to specific parametric function or just B-spline or natural cubic splines. Any function of time can be included in the linear predictor of longitudinal models. So that's very convenient, and it's also quite an important thing because when we fit joint models, sometimes we need to evaluate the longitudinal outcome, the linear predictor for the longitudinal outcome at many time points to include it in survival. And we can do this by simply providing the functions of time, and they can easily be dealt with internally, and we can account for them in the joint model too. So that's really a nice property of this. We can also handle a large number of random effects. So I think now the limitation is 24 correlated random effects, which is huge. No one needs that many random effects correlated. That's hundreds of hyperparameters, but we have to put a limit, and it's not even a hard limit. We could go beyond, but it's not really useful unless someone needs it for real. But for independent random effects, we don't really have a limitation. You can have as many as your computer can handle. So the limitation will be the power of your machine. So no restrictions on random effects, or very little restrictions compared to alternatives. And the last point is we can have random effects on multiple hierarchical levels. That's also interesting because usually we have random effects at the individual level, but we could also, on top of that, include random effect on, I don't know, hospital level, department level. We can have multiple hierarchical layers to account for random effects in the same model. When we have multiple outcomes, we can have multiple longitudinal models, and they would be linked by correlated random effects. Again, this is just the gold standard, but we could think of different associations. So the value of one marker could depend on the value of another marker. We could have any association. Here I just developed correlated random effects because that's what people usually do, but it's not really a limit. We can do more. So let's look at one example. If we consider 3 longitudinal outcomes, the first one being continuous, second one being counts, and last one being a binary longitudinal outcome. Let's say we want to fit a mixed effects regression model for each of those 3 outcomes. So we have some parameters. Beta would be fixed effects, and B will be random effects. So here I only included one random effect in each, a random intercept, just for simplicity, because I could include random effects for time and functions of time, but that would make the slide difficult to read, so I kept it simple. So we have fixed effects on the intercept. We have 2 functions here, f1 and f2. Those are 2 bases for natural cubic splines, so 2 basis functions associated to fixed effects. And we have treatment effect at baseline, treatment effect over the first basis of spline and the second one. So we do this for each model. So we have like 6 fixed effects and 1 random effect for each of the models. And the relationship between those 3 models is based on the correlation of those random intercepts. So a 3 by 3 variance covariance matrix. So I simulated data from this model. You can see the data here, where each individual now has multiple lines. So individual 1 measured at time 0, individual 1 measured at time 1, and at time 2, and then individual 2, etc. And for each of those time points, we have measurement of our 3 outcomes. We could have missing data in any of the outcomes, it's fine. But here I just simulated fully observed data. So you can see our continuous outcome, the count one, and the binary one here. So to fit this model, very simple. We just use the same joint function, but this time it's a formula for longitudinal, which is a list with 3 entries for our 3 mixed effects regression models. And then we have the family, Gaussian, Poisson, and binomial. The core long arguments specifies that we want correlation between these 3 random effects. And then we just give the ID column, the time column, and the data set. That's it. So I won't show the summary because it's just a bunch of parameters. It's not so interesting, but I will show what happens when you plot a fitted model with INLA joint. So you will get a series of plots that basically show the posterior marginal of all the model parameters. So this is the first plot. It's only the first longitudinal outcome, L1, where you have the fixed intercept, the 2 basis spline effects, the treatment by spline, and the residual error variance. I added the true value as a vertical dashed line here just because I simulated data, so I know the true value, but in practice, you won't see this if you apply inner joint. So this is the first plot, fixed effects. We have the same for the second outcome, the count one, and the third one, which is binary. So I won't show them, but we have 3 series of plots for the fixed effects. Then we have random effects. So here we have 3 random intercepts on the diagonal, and we can see the posterior marginal distribution of their variance. Off diagonal is the covariance between those 3 random effects. But I'm not a big fan of variance and covariance because it's very difficult to interpret them. So I'm usually more familiar with standard deviations and correlations. Within that joint, we can easily switch by simply adding to the call of the plot SD core equal true. This will convert any variance into standard deviation and any covariance into correlation. And this is also valid for summary. If you add SD core equal true in summary, you get the result with standard deviations instead of variances. So here we have standard deviations and correlation. Another feature is priors equal true. You can see I added this in my call of the plot function. This will display priors on top of posteriors. It's very important because this allows to do prior sensitivity analysis. This allows to identify whether one of the parameters of your model is actually relying on no data, and then you want to tackle this issue. So this is very important to be able to display priors on top of posteriors, and you can see how the posterior, which is the straight line, are driven by the data, where the prior was non-informative. So if you look, for example, at this is the correlation between the intercept of the first and third outcome, so the Gaussian and the binary one. The prior is this flat Gaussian shape that basically says, oh, if there is no data, the most likely correlation is 0, but it's quite flat, so it allows for any correlation between -1 and 1, assuming there is enough data. So you can see here, my posterior is data-driven because the true value is -0.5, and that's what the data says. Okay. So now we might be interested in predictions, but this model, as opposed to the competing risk one, is an individual level model because we have individual random effects. So we might want to do individual predictions, which can be done with the same predict function. So what I did here, I simulated some new individuals. So here, it's a new data set with individuals that were not present when we fitted the model. So individual 1 here is not the same as individual 1 that I used to fit my model. And for each of these individuals, I simulated some data points. The black points you can see on the plot. So we have 4 new individuals. So for each of them, we have some observations. And we could also have some missing data here. We could predict only conditional on the first outcome. And we will predict for the 3 outcomes because the model includes those 3 outcomes. Here I again included full data, but there is no problem to have missing data here. So you can see the results. The black straight line is the predicted trajectory based on the points, the new points we observed. The red dashed line is the true underlying trajectory, and you can see the shaded area, which is the 95% credible interval around the true value. What does it mean? It means free from residual error, basically. We predict the true value of the marker, so this uncertainty is quantified around the true value. If we want to have uncertainty around observed values, we need to include the residual error. And this can be done by adding res r long, residual error in longitudinal, to true. And this will just make the credible interval of my predictions include the residual error such that 95% of the observations will be in the interval. So you can choose either predicting over the true value or the observations, basically. So those results are just for the continuous outcome, but if you remember, we have 3 outcomes in this model. We have also the count and the binary one. So when we predict for the entire model, so we get also those trajectories for count and binary, but it's more difficult to picture observed versus fitted because, for example, the binary is either a 1 or a 0. What we fit is the probability of 1 versus 0. And this is done on a continuous scale with a nonlinear log link function. So what we can do, we can add this inverse.link equal true in the code of my predict function, such that I will apply the inverse link function for any generalized linear model in order to be able to compare the fitted versus observed data. So for example, here I'm predicting directly the rate of the Poisson instead of predicting the linear predictor. So I can compare my Poisson observation, my counts, to the rate of the Poisson. Same for binary here. I'm predicting the probability of 1 versus 0. So I can directly compare my observations, which are 1 or 0, versus the probability of 1 versus 0 that may evolve over time. Okay, so we have discussed survival models, longitudinal models. We don't really need INLA to fit a proportional hazard model or a mixed effects model. But those are ingredients we can use to build joint models. And that's the main purpose of my work, to be able to build joint models based on longitudinal and survival outcomes. And those models are very interesting. I could spend an hour explaining why, but I will focus only on those couple bullet points. Basically, joint models can help reducing bias from informative dropout. We can increase statistical efficiency because we use all the available information. We can handle endogenous time-varying covariates. And we can compute individualized dynamic risk predictions. So there are many things we can do with joint models that are very useful for biomedical research. And that's where INLA is the most interesting, actually. So since I already introduced longitudinal and survival model, you get an idea of what we can include in a joint model. For example, we could combine the competing risk model with the multivariate longitudinal model and have a fancy joint model with 2 survival and 3 longitudinal outcomes. That's totally feasible. The question is, how do we link them in a joint model? And this is based on some association structures that I will introduce now. So we have multiple options. The first one being shared random effects, where, for example, the random intercept, the random slope can be shared from a longitudinal mixed effects model in a survival proportional hazards model. And this will answer the question, does an individual's underlying trajectory affect their risk? We can have the current value, where the entire time-dependent linear predictor is shared, and it answers the question, does the current true value of the marker at time t affect the risk at time t? We can share the current slope, which corresponds to the derivative of the linear predictor according to time. That means, does the current rate of change of the marker affect the risk? So it's about the rate of change instead of the value itself. And finally, the cumulative value, which is the integral of the linear predictor. And it answers, does the cumulative exposure to the marker over time affect the risk? So each of these association structures, they will answer a different question of interest. So when you build a joint model, the structure of the joint model should be defined by the clinical question you're trying to answer. If, for example, I'm interested in the relationship between the number of cigarettes smoked per day and the risk of lung cancer. If I assume a current value, I will assume that the number of cigarettes I smoke today are explaining the risk of cancer today. It's a bit of a nonsense. I would rather explain the risk today by the number of cigarettes I have smoked over the last 5 years, for example. So this would be a cumulative value where I integrate over the last 5 years or any specific window to evaluate whether it has an effect of the risk of event today. So we can do very nice things. However, there is one limitation here. All of these associations, when they are shared in a survival submodel, they're associated to a fixed effect, basically. Basically, we mean the effect is log linear. It's linear on the log scale in the hazard ratio. So this is a limit because if we think, for example, the relationship between body mass index and the risk of death from any cause. If the longitudinal measurement of body mass index, if we have a high value of BMI, like morbid obesity, we have an increased risk of death. All right? But if we have a low value also, we again have an increased risk of death. So the relationship is not linear, it's quadratic. It has a U shape, right? So if we assume a current value, we are doing something wrong. In the left plot here, you can see I simulated some data where we have this type of shape. So the x-axis would be the BMI, and the y-axis is my corresponding hazard ratio. You can see that for higher value or lower value compared to 0, which would be my average value, we have an increased risk of death. The hazard ratio increases. If I fit a standard joint model on this data, I get the result as the dotted line, the red dotted line here. It says there is no relationship between BMI and the risk of death because it cannot choose between the higher risk for higher values or higher risk for lower values. It's completely struggling because it lacks flexibility. So we have implemented a way to increase flexibility by adding on top of the linear a quadratic effect. This allows to have the value of the hazard ratio depend on the value of the component being shared, for example, BMI. And you can see the green curve here, it perfectly captures this U shape. And the quadratic could also capture an inverted U shape. But this is still a bit limited. For example, if you look on the right, I simulated some data where we have a marker that is shared. And for low value, like below minus 0.5, you can see the hazard ratio is below 1. So this is a beneficial marker, right? But for high value, you can see the hazard ratio becomes higher than 1. So it becomes deleterious. So depending on its value, we will have either a beneficial effect or a deleterious effect. This is very complex. And if you fit the standard joint model on this, the answer is there is no relationship because it lacks the flexibility. And it's the same for the quadratic. It's not flexible enough to capture this shape. So we added even an additional layer of flexibility by allowing deviations from the quadratic. So this allows to capture very nonlinear association, and there is no restrictions. We can capture any shape, basically, as long as there is enough data to identify it. So this is really an important feature because it not only allows to fit nonlinear relationship, it also allows to verify the linearity assumption. Many people use joint model and they assume linearity in the effect, which may be wrong, but no one has verified because there is no tool to verify. So this is a tool that allows to verify, and the reason is because those are built hierarchically. So the linear is included in the quadratic, and the quadratic is included in the spline. So you can compare those models with goodness of fit criteria, like BIC, DIC, WAIC, whatever. You can check, is it worth adding flexibility to my association or not? And there is a metric to quantify if it's worth or not. And one point, all those associations can be associated to a nonlinear effect. This is compatible with all those quantities. So we can have a nonlinear effect of any of those quantities. That's also an important feature. Okay, let's get back to the joint modeling. I want to show a very simple example of a multivariate joint model, so you get an idea of how we can combine longitudinal and survival in one single call of the joint function. So I'm considering one continuous outcome on the log scale, a log normal model. So this is longitudinal with fixed intercept, random intercept, fixed effect of time, treatment, time by treatment, and some residual error. Then we have some counts fitted with a mixed effects model again. So I only have random intercepts here again for simplicity, but of course we could have more random effects in each of those models. And the interesting part is the event risk. We have a proportional hazard model where the risk of event for individual I at time t depends on the current value for individual I at time t of the first marker and the second marker. So we have two time-dependent components that are being shared here. So to fit this model with INLA joint, we have the joint call where the formula for longitudinal is a list of two formula for my two longitudinal outcomes. Then I have my formula for the survival outcome, the data set for each, because we have only one line per individual in the survival, while we have multiple lines for repeated measurement in the longitudinal, so we have two different data sets. The columns to identify ID and time. The baseline risk here is a random walk of order 2. The family. We have correlated random effect between the two longitudinal, and the association here is current value. So the first longitudinal shares its current value in the survival, and the second one does the same. So this model, I fitted with INLA joint, and I also fitted it with the best available alternative. Earlier in this talk, I showed some comparison between INLA and JAGS and STAN. Actually, there are some software specialized in joint models. Particularly, GEMBISE2 is an amazing package. It's the best one to do Bayesian inference with MCMC. So I wanted to compare the results we get for this model, this one, within a joint compared to GEMBISE2, and also RStanArm, which is using STAN, which is much slower, but it's also an interesting package. The takeaway message here is INLA joint is very fast, but it's also very accurate. We get exactly the same results. So there is no trade-off. We just have faster results. So here are the parameters. We have the fixed effects for the first longitudinal, fixed effects for the second longitudinal, the survival, so effect of treatment, the association between the two longitudinal and survival, the standard deviation of the longitudinal, which is continuous, and the variance covariance of my random effects. So to go beyond, I also, from the same model, did some simulations to show how the computation time scales with the data size. So I started with 100 individuals. I simulated data. So we have two longitudinal markers, so that's a lot of longitudinal measurements. The total data size is around 928. And then I doubled the sample size, and I doubled until reaching the limit. And I compared INLA joint with GEMBISE2. So you can see the two curves are quite parallel, but the y-axis is on the log 10 scale. So that means the difference is increasing exponentially. You can notice some convergence error, which is a bit random because I'm simulating from the true model. So we expect the estimation to be well behaved, but that's a property of iterative methods. Sometimes they just fail, and here I'm not even sure why. I couldn't fix it. So that's a feature. INLA joint is much more stable. And after like 50,000 individuals, 400,000 observations, GEMBISE2 reached the limit of the machine available, and then it's out of memory. So it took 8 hours here, while it takes only 1,000 seconds for INLA joint for the same model. And we can go beyond. With INLA joint, we managed to reach 400,000 individual, 3.5 million data observations, and that takes 8 hours. And this is a limit from the machine, but if you increase the machine, you can go beyond, of course. Okay, so the last point I want to mention is spatial models. This is a bit new. I didn't publish anything yet, but it's very interesting because health outcomes and their predictors, like air pollution, they are often spatially correlated. And this can be driven by unobserved confounders like socioeconomic factors. And our framework, it allows to capture this spatially structured data with random effects. And those can be included in any component. It can be in a longitudinal model, in a survival, or in a joint model where we have a spatial random effect that is shared on scale. We can do very interesting things. And this is very useful because INLA has been, as I mentioned in the beginning of my talk, it has been developed widely for spatial and spatiotemporal data analysis. This is very efficient for this framework. Now that we have also the joint models or longitudinal and survival, we can combine those two, and it's really unique. INLA can fit these models, and it's very useful because when we have some spatial autocorrelation, let's say air pollution is measured at different points, we know that two points very close to each other will have very similar value. So if we just use a normal random effects, IID, we will lose some information. So this is very important to be able to capture this spatially structured correlation, like it can capture some unobserved confounder like socioeconomic factors, and including this in the model is the same as when you include a random effect for the individual level. You know that the same measurement, the measurement for the same individual, they are correlated. That's why we include random effects in longitudinal data. It's the same idea when we have spatially structured data, and it's often the case for health outcomes, so it's very useful. And we have two different frameworks for this. In one case, the data is aggregated over regions. And in this case, we will use the Bizag-York-Mollier model for aerial data. So this is a map of mainland France, and each department is associated to a value of the random effects. But you can see neighbors are more likely to have similar values. So there is some spatial structure. That's the whole point. When we have data that are tied to specific coordinates, not aggregated over region, we can use stochastic partial differential equation models. So they are referred to as point reference models here. So basically, we map a continuous field, a continuous spatial field that has no border. And we can learn from data at any point, and we can predict for data at any point. So it's very flexible as it's continuous. So it's a very interesting approach. For example, if you have air pollution measured at specific stations, we can map it to have a continuous field, and then you can evaluate the risk for an individual at his specific location based on the surrounding data. So just a toy example to illustrate, I didn't show a lot for the spatial because it's very new and also a bit complex. So here I'm just showing a simple survival model where we have an individual I with a risk at time t. And this risk will depend on some fixed effects, and we include a random effect at the spatial level, here the department level. And then with INLA joint, we can compute predictions, for example, conditional on a specific location. So here I picked the department with the lowest risk and the department with the highest risk, and we can get survival probabilities over time conditional on this location. So it's very nice. We can do very interesting things and very promising framework. So to summarize, this framework handles complex data. It unifies the analysis of longitudinal, survival, multivariate, and spatial outcomes. It is computationally efficient. The INLA methodology is fast and accurate, and it avoids the high computational cost of MCMC methods. The implementation is accessible through the INLA joint R package, which uses this building block syntax that allows to build a joint model that includes any number of longitudinal or survival submodels. So it's very flexible. And we can compute dynamic predictions. The predict function took me an eternity to write. I took like 2 years on it. Basically, the idea is to predict anything from a model, from any model, conditional on any data. It's very flexible, so that's a very key point of INLA joint. A quick word about INLA, because it's the core engine of this work. INLA is a freely available method that is open source and available as an R package. It has been proposed in 2009, and it has been evolving a lot since. In 2023, we proposed a new version of INLA called the modern INLA. It completely replaced the previous one because it's uniformly better. It's much faster and scalable for large data. The reason is because we decoupled the latent field from the data size. So before the original INLA, the more data you have, the bigger the latent field becomes, and we easily reach limitation. We couldn't do big data with the old INLA. Now it's completely independent, so we can make very big data applications. I showed an illustration with 3.5 million, but we can do 20 million even. We have some simulations. So it's very a big improvement in 2023, and it keeps evolving. Next year, we will have a new compute engine that will be replacing the current one in INLA. So currently, we use an open source solver. We used to have Paradiso, which is a private solver, but they started charging for using it. So it's not free to use anymore. And we are very attached to INLA being open source. So we get back to the original open source library. And now we are building our own library, S-Tiles, which will be open source. And it's actually outperforming the pay-to-use one. So this is a huge progress. And you can expect all the computation times I showed today to be divided by 2 next year. This is a huge improvement, and at least 2 because we have simulations that show we can gain up to 10 times faster. But for the biostatistical models I showed today, I expect an improvement of 2 times faster, which is already huge. And we have some projects. Currently, INLA works on CPU, but we are extending it to work on GPU and to have distributed computing over multiple GPUs. So this will also be a huge step forward for scalability. Okay, thank you for listening. I'm happy to answer any questions.